Hi, folks, and welcome back. I know it's been a little while since you had the last video, but time to move on. It's taken a little bit of time to get everything together. The coronavirus is really putting a dampener on everybody's lifestyle these days, but we will get through this together. So, having already had this chapter presented in the classroom, I'm going to go through very quickly the highlights of Chapter 2, the atmosphere. I'm also going to invite you to look at some of the links that are on your Canvas shell under modules. So make sure to look at those. So here we go, Chapter 2, the atmosphere. Okay, definition now. Atmosphere is that gaseous envelope surrounding the Earth. It's mainly gases, but there's also some liquids and some solids in there too. So before we analyze what gases are in there, we need to take out the solid particulate matter, the liquid droplets, and the water vapor, and we'll see what happens once we do that. So these are some of the solid particles that you would probably see in the atmosphere or experience in the atmosphere. Dust particles, salt, soot, pollen, volcanic ash, ice. Most of these, of course, are coming from the surface of the Earth and being blown upwards, but some of them are also coming from outer space, the cosmic dust. So we have to account for that too. But keep in mind later on, when we talk in chapter 3 about the process of scattering, these are the solid particles that we're referring to in that process. Again, that's in chapter 3. So once we take samples of air and we extract the water vapor, the liquid water droplets, and the solid particulate matter, what we're left with is referred to as dry air. And if we take those samples anywhere in the lower atmosphere, no matter where you are on the planet, pretty much you're going to end up with three main gases. And we call those, of course, the three main gases. Also, because their concentrations don't vary, it's always the same, they are referred to as the non-variable gases. And we'll see from this pie chart and also from the numbers here that the air that you breathe, once we've taken out the particulate matter and the water, 78% of that is nitrogen in the form of N2, that's two nitrogen atoms bonded together to make a nitrogen molecule. That's 78% of what you're breathing in and what you're breathing out. The second main component is oxygen in the form of O2. So two oxygen atoms bonded together to make an oxygen molecule, O2, and that represents 21% of dry air. And the third main gas is argon. It doesn't like to hang out with anything, even itself. So argon we find by itself making up 0.93% of dry air. The chemical symbol for argon is Ar. If we add those up together, by the way, 78, 21, and 0.93%, we end up with 99.93%. So almost everything that we're breathing in and breathing out is nitrogen, oxygen, and argon when we're talking about dry air. Just a quick reminder, nitrogen, 78% of dry air, is continuously recycled from the atmosphere by rain into the soil, and then plants and bacteria go to action, and upon plants growing and absorbing that nitrogen, animals eating it, and then defecating, goes back to the soil, ultimately back into the plants, and we get a recycling when the nitrogen is consumed by bacteria and released back into the atmosphere. So continuously going back and forth and back and forth. We do need nitrogen in order to grow for our DNA and our RNA, but we don't get it from the air. We get it from eating. So basically, yes, we need it, but we don't get it directly from the atmosphere. We rely on plants to do most of that work, and then we eat the plant. Oxygen represents 21% of dry air. Again, that is coming from photosynthesis. It's been going on for billions of years. Our early atmospheres, they formed, they blew away, they formed. Basically, for about 3.5 billion years, we've had oxygen in that atmosphere. And slowly over time, in ebbs and flows, we've had a oxygen-rich environment. We need that. We couldn't have life as we know it without it. So it's very important that we basically do everything we can to maintain the things that are producing this oxygen for us, and that would be our photosynthesizing plants and algae, etc. So forests in particular, they're very worthwhile saving. Well, maybe it's going to save us one day too. Okay. The photosynthesis process really quickly. Basically, it's saying that from the atmosphere, we're getting the carbon dioxide into the plants. The plant is also taking up water through the roots and nutrients through the roots. So the plants are basically taking in the CO2 and they're letting out oxygen. And in the process, they're building up themselves, the proteins and carbohydrates and sugars, etc. So you imagine plants like this growing in a swampy environment. Now, if you think back in time, we had lots of shallow seas and shallow swampy environments, lots of plants growing hundreds of millions of years ago. And as they grew, they were sucking out the carbon dioxide from the atmosphere, and basically they were growing and building themselves. Now, what would happen to those plants if they fell down into a swamp, got buried by the water so they can't decay very quickly? And it's in an area where geologically the whole area is sinking down. So the water could get filled up with this decaying plant material, but also some silt and sand washing in, burying those layers. We would see over time that we get layers and layers and layers of this buried plant material. That would turn into something called peat, and if enough geologic time, pressure, and overlaying strata would actually turn that into different forms of coal. But this is really how our coal forms. We take carbon dioxide out of the atmosphere through photosynthesis, and then we bury those carbon molecules away with the fallen plants. And if that was going on for tens of millions, maybe even hundreds of millions of years, we would get thick accumulations of coal. Later on, those would get buried. We would go find them, dig them up, extract the coal, burn the coal, and then release that really old carbon back into the atmosphere through that combustion process. And that's part of what is an issue these days. We're taking old sequestered carbon that's been underground for many, many years and releasing it back into the environment. More on that to follow here. Our third gas here is argon. And argon, again, doesn't like to mix with anything. It comes from the decay of potassium in the Earth's crust and doesn't like to mix with anything. So you breathe it in, you breathe it out. Enough about argon. Now, if we add up the 78% for nitrogen, 21% for oxygen, 0.93% for argon, that only leaves 0.07% remainder. So all the other gases we talk about are occupying that very small space between the other molecules in the atmosphere. But they also don't require too many of those molecules to do some significant change or damage to our atmosphere. So we're going to look at some of these trace or variable gases. We call them trace because there's just a hint of them in the atmosphere. We call them variable because their concentrations do change from place to place and time to time, unlike the main gases or non-variable gases. So for all of the trace gases, we need to know, are they responsible for ozone depletion? That is depleting our natural ozone layer. Are they responsible for global warming / climate change? Again, more on that to follow. We just had an intro to that. Or are they responsible for acid precipitation or acid rain? I say precipitation sometimes because it could be acid snow, it could be acid sleet, but the most common form of precipitation is rain, so we can get away with saying acid rain and really using those as synonyms. Okay, so here's a little chart of our trace gases, color-coded as a little reminder. One of the main things I want you to know is which of these gases are greenhouse gases. Again, greenhouse gases. You'll know what that process is in just a couple of minutes. But I'm using the color green here to show which of these gases are greenhouse gases, or at least related to it. For instance, water vapor is a natural greenhouse gas, but we haven't really increased the amount of water vapor in the atmosphere, so it's in a kind of a separate category. Yes, it's a greenhouse gas. It's a very effective greenhouse gas, but it's more natural than not. Carbon dioxide, on the other hand, is natural in our atmosphere, but we have really increased its concentration. So CO2 is carbon dioxide. O3 is ozone. It's just 3 oxygen atoms bonded together to make a single molecule called ozone. It has a very tiny concentration. There are 2 forms of it, and we'll get into those 2 forms in just a minute. CH4 is methane. Methane is like natural gas. It's found in the atmosphere naturally from decomposition within swamps and other wetlands, rice paddies, etc. We can consider rice paddies to be natural. They've been part of our ecosystem now for thousands of years. Very tiny concentration also. Now this one is not in green, so it's not a greenhouse gas. This is oxides of sulfur or sulfur oxides. So sulfur and oxygen bonded together to make various forms of of sulfurous and oxygenated molecules. Very tiny concentration also. NOx, that's oxides of nitrogen or nitrogen oxides. Again, a very small concentration. The green shows that nitrogen oxides are a greenhouse gas, but also we have some red on here. So what is that red all about for sulfur oxides and nitrogen oxides? They both have some of that. Well, if you were to put a piece of litmus paper into a solution and that litmus paper turns red, that tells you that the aqueous solution that you're checking out or testing is acidic. So red is symbolic of an acid. So when we're talking about acid rain, we're looking at oxides of sulfur and also oxides of nitrogen. These are the two gases most responsible for acid precipitation or acid rain. So we can see also NOx, also a greenhouse gas. And lastly, CFCs, chlorofluorocarbons, very tiny concentration. And CFCs are not only a greenhouse gas, but they are most associated with depletion of natural ozone in the stratosphere, that second major layer of our atmosphere as we go upwards. And we'll learn more about those layers at the end of this chapter. But CFCs definitely make that association with depleting that ozone. So ozone depletion is what we're looking at there. All these letters you see here, ppm, that means parts per million. The only one I really want you to know what the concentration is the one for carbon dioxide, 410 parts per million. So out of a million parts of air, 410 are currently carbon dioxide, but that number is increasing about 2 parts per million every single year. And I do want you to know the concentration of water vapor, about 0 to 4%. More on that, again, in just a minute. So, or less than a minute. Here we go, water vapor. So water vapor, H2O, has a concentration ranging from almost zero water in the atmosphere. We find that in the very driest places on the planet, like in the Atacama Desert of Chile, and also the McMurdo dry valleys of Antarctica. So very cold places tend to be also very, very dry places. And the McMurdo dry valleys are actually the driest place on the planet. Never known to have been any precipitation there in our lifetimes. 4%. Well, where would you get 4% water vapor in the air? That's going to feel pretty darn humid. So we're looking at tropical rainforests and in particular the oceans. So the tropical oceans, imagine, where does the water come from? Well, it comes from very wet things. What's the wettest thing you can hit? Well, water. So a tropical ocean, the sun beats down on it, it's going to evaporate a lot of moisture into the air. So very moist air over those tropical oceans. Rainforests also have a recycling method that keeps that water going from the atmosphere, precipitating in the form of rain down to the forest, back up again when the sun comes out, etc. So the source of this is certainly evaporation. Most of this water will stay in the atmosphere for a few days before it precipitates out. Are we worried about it? No. No one's ever said, oh my gosh, it's about to rain. Be careful, we're going to dissolve. But, of course, rain can be light and rain can be heavy. So there are some aspects of that we'll talk about in our very last chapters when we're looking at flooding. So, not a problem, but it also does accentuate some of the other gases and their ability to act as a greenhouse gas. So water's kind of in a little funky mode there. It's not really something we worry about, but if we were to put significantly more water vapor into the atmosphere, then we start to get a little worried. So what is that greenhouse effect? Well, basically the sun is 93 million miles away or so on average, and the sun is going to emanate energy in all directions, but about half of a billionth of 1% gets to that, half of a billionth of the total amount gets all the way across space and intersects our planet. So short wavelengths coming down from the sun can make their way through the atmosphere, not a problem. The Earth is going to absorb almost half of that at its surface, about 46% of the incoming solar radiation that emanated from the sun that got to the top of our atmosphere, about 46% of that total will actually get absorbed at the surface of the Earth. The surface of the Earth heats up. Because the sun is so much hotter, its peak energy is in the short wavelength portion of the spectrum, but the Earth can only heat up to an average of about 60 degrees Fahrenheit, and then it's going to re-radiate back into space these long infrared wavelengths, otherwise known as infrared energy or thermal infrared or heat energy, long wavelengths back into space. But it still has to get through our atmosphere. Now, the same atmosphere that let the short wavelengths through don't let those long wavelengths out so easily. It tends to trap that heat energy in this layer. So that's going to tend to allow the Earth to heat up and slowly give off that heat. For this reason, we don't see temperatures plummet right when the sun goes down. We get slow, for most environments, slow cooling down overnight because these gases tend to help trap that energy. But what are those gases? I don't know if you can see right here, but it says CO2, so carbon dioxide, H2O, water vapor, and CH4, methane. So these are the main gases. They have been in our atmosphere in various concentrations for pretty much hundreds of millions of years. So they've been naturally going through this process for those same hundreds of millions of years. Now here's the issue. What would happen if we increase the concentration of CO2? If we increase the concentration of water, which we're not really doing, increase the concentration of methane. And that is exactly what we're doing. So we are accentuating this greenhouse, this natural greenhouse effect. We are basically enhancing that natural greenhouse effect. We are changing the temperature of the lower atmosphere because more heat is getting absorbed down here. And there's all kinds of follow-on effects from that. So it's going to affect the climate. We call that climate change. It's going to warm the lower atmosphere. We call that global warming. We're going to enhance the natural greenhouse effect, and we call that enhanced greenhouse effect, or sometimes the anthropomorphic greenhouse effect. We're going to weird up everything in the climate. Some people refer to this as climate weirding. It's actually not a bad name. So things are changing. Let's see what and why and how. So we do have some experience here. Here's our planet right here, just the Goldilocks effect as far as distance from the sun and the right amount of trace elements in our atmosphere. If we had way too much carbon dioxide, like Venus does, and it's very, very warm there, or too little, like Mars, where it's very, very cold, we'd be in big trouble. We'd be considerably warmer or cooler than we are right now. But with the CO2 and methane levels and water vapor levels we have right now at the distance from the sun, we actually are maintaining temperatures very close to about 60 degrees Fahrenheit on average, but that is increasing because we are putting more of that CO2 and methane into the atmosphere, something we all are starting to worry about. So what happens if we put more CO2 into the atmosphere? Well, current concentrations are 410 parts per million in 2020, increasing about 2 parts per million per year. Now, there is an up and down effect because the northern hemisphere has a lot of land-based plants, and those tend to photosynthesize part of the year, and then they kind of go dormant for the rest of the year, and that's going to have an impact on the amount of CO2 in the atmosphere. We can still, and we will take a look at that in a second. But the sources of CO2 come from burning of wood, burning of coal, burning of oil, burning of gas, pretty much burning of anything. The product of burning or combustion is CO2 going up into the atmosphere. We do have natural sources like the outgassing from volcanic eruptions and also from natural forest fires. But we see an awful lot of deforestation where we're taking whole forests out for making furniture, for making or using firewood, but we're basically clearing forests. Now remember, forests and other plants are the natural vacuum cleaners for CO2. If you think back a few slides, we were looking at CO2 being pulled out of the atmosphere by plants, and plants releasing O2 in the process of photosynthesis. So if we remove the forests in large numbers, we're removing big vacuum cleaners for CO2. And then if we burn those same trees that were part of the forest, we're releasing extra CO2 to the atmosphere. That's problematic. If we dig down and extract the old fossil fuel, coal, oil, gas, and then burn those and release that carbon into the atmosphere, we're putting back into the atmosphere carbon that was pulled out hundreds of millions of years ago. There's bound to be an impact from that. Well, we worry about CO2 so much because it is responsible for 63% of all the extra warming that's been going on through the industrial age and probably back to the time of the Romans, just not at the scale that we're seeing right now. Once the CO2 is in the atmosphere, it stays there for an awful long time, over 100 years, so we can't pull it out easily. Some of it does go up into the atmosphere, it gets pulled into the oceans, so luckily the oceans can pull some of this out. But on the bad side or downside, that extra CO2 turns into carbonic acid in the oceans, making the oceans more acidic, and then that kills off our coral reefs. So we see multiple stages of impact here as we look at CO2 in the atmosphere. Again, our current concentration, 410 parts per million, but we can look back in time and see that for the last 650,000 years, probably 800,000 years, possibly even the last 3 million years, carbon dioxide concentrations in the atmosphere never got below 180 parts per million and never went above 300 parts per million. Let's explore that here in just a second. Well, okay, sources of CO2, deforestation, industrial pollution, burning of stuff, and cars. Behind my big head here, it does say CO2. So transportation, burning gas, burning diesel, things of that nature. And as we look at this, you might want to think in your own life, what can you do to minimize your CO2 footprint, or how much CO2 you are actually emitting as an individual every single day? Every little bit adds up, because if every single person did a little bit, you times that by 7 or 8 billion people, and we've got some changes we can make there. We can all have an impact. Okay, extra methane. Well, methane is the number 2 greenhouse gas. Methane comes naturally from maybe the decay of organic material in natural wetlands, but also in swamps and rice paddies. So anytime we have a swampy or rice paddy environment where the water sits still and vegetation falls down into that still water, it cannot decay very easily. Anaerobic bacteria, so the bacteria that's prevalent in oxygen poor environments, tries to degrade that organic material, and it produces little bubbles of methane in doing so. Again, you bury those swamps or those wetlands, over time those can get turned into that peat or coal, and basically trap not only carbon in there, but also methane. The primary constituent of natural gas is methane, so if you're burning natural gas, methane is going to be released. Again, the number 2 greenhouse gas, responsible for 18.5% of all extra warming associated with climate change or global warming, and residence time of methane is about 12 years. So when we release it, it's still another dozen years until it's still in the atmosphere. U.S. Greenhouse gas emissions between 1990 and 2017, we can see basically enteric fermentation is basically in the guts of cattle, and also in termites. They act just like a swampy environment, and methane is produced here. Natural gas and petroleum systems, so basically extraction of natural gas, extraction of petroleum, are responsible for an awful lot of emissions. Landfills, this is all for methane, by the way, just methane. Landfills, so I don't know if you've ever seen a landfill, smelled a landfill, methane is being produced there, and sometimes they'll even be burning that methane off with a flame. Other times they're trying to capture that as a fuel source these days. Coal mining, so you can see the extractive industries, agricultural industries, and also landfilling our own waste are big producers here. If you've ever driven up Highway 5 or Highway 99 up towards San Francisco, about halfway near Kettleman City, you can all of a sudden smell that nasty stuff in the air, big piles of manure, and methane is being produced there. If you've gotten too close to cattle, you've smelled methane before. Well, actually, let me rephrase that. You can't actually smell the methane, but you can smell the organic material that's associated with it. So again, extra warming associated with climate change, 63%. Carbon dioxide is responsible for that extra warming. Methane, 18.5%. We also have some other gases like CFCs and oxides of nitrogen, etc. But why do we concentrate on methane and CO2? Those are the big contributors to this extra warming and all the issues that are associated with it. So this graph over here, the one on the top, shows us CO2 concentrations going back over 600,000 years ago. You see this pattern here, concentrations, the higher up, by the way, the higher up is a higher concentration. So this is 600,000 years ago, 100,000 years ago, and this is pretty much present day. And concentrations of CO2 went up, down, 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 up, kind of like in a heartbeat pattern. And we know why this is. It's largely because of interactions between the Earth and the Sun changing on these predictable cycles called Milankovitch cycles. And they basically equate to just over 100,000-year cycle of these warming periods and cooling periods. So slow cooling, fast warming, slow cooling, fast warming, slow cooling, fast warming. Let me show you that. So we got fast warming, slow cooling, fast warming, slow cooling, fast warming, slow cooling, fast warming, slow cooling, fast warming. Okay. Now, throughout this time period, I've already there equated warming. My apologies, I jumped a step ahead. The warming and cooling are associated with CO2 levels. So excuse my jump there, but basically what we're seeing here are CO2 levels, and I've got to show you the associated temperatures in just a second. That's the red line, first of all from ice core measurements, and later on from direct measurements up here. So I should have said CO2 up, down, up, down, up, down, up, down. And then we see temperature correlated very well with the CO2 levels, up, down, up, down, up, down, up, down, up, down. So again, CO2 and temperatures are acting in concert with each other, basically. CO2 goes up, temperature goes up. CO2 goes down, temperature goes down in this pattern here. Now, nobody was around, even let's say 20,000 years ago, to measure CO2 or to measure temperature. No one was around 100,000 years ago to do that, 200,000 plus years ago, 300,000, 400,000 years ago. But we don't have to do that. Every time it snows, and that snow will stick around, the snow has the capacity or the ability to trap air between each of those flakes of snow. Now, if you have snow on top of snow on top of snow, those gases get trapped inside the snow layers as bubbles. And as that snow turns to ice, those bubbles get trapped within the ice. So we could actually drill down in places where ice has been around for a long time, like Antarctica, drill down and basically get a very good idea of two things. What's in those bubbles? And then more specifically, what was the temperature when those bubbles formed, when that snow formed? So we can figure this out based on the isotopes of oxygen. Oxygen has three different main varieties: oxygen 16, oxygen 17, oxygen 18. And basically the ratio of those will tell us something about the temperature when the air that formed that snow formed. Also, the bubbles will also trap the CO2 in there, so we can directly measure that CO2 from those bubbles. So we can find out what the CO2 levels were, what the temperature was, CO2 levels, temperature, etc. So again, we didn't have to be around to do that. We have these proxy measures of what the temperature and CO2 concentrations were in the atmosphere hundreds of thousands of years ago. One thing to keep in note here, we do make direct measurements now. And this slide is a bit dated, but from 2006, you can see direct measurements were as high as 382 parts per million on the top of Mauna Loa in Hawaii. So there's an observatory there, and they can make direct measurements there. So you can see at this point, we're way off the scale. We used to be no higher than 300 parts per million, and all of a sudden, we're way up here. Something is going on. So the ice cores tell us a long-term record of CO2 and temperatures, and we can make direct measurements now of both CO2 and temperature. So historic correlation between CO2 and temperature, going back again, we see on this graph, one goes up, the other one goes up. These are very well correlated with each other. Again, from the ice cores and now from direct measurements. Sifel Ice Core Station is one of those stations in Antarctica. It's no longer operational. I was only there, I think, from the 70s to the late 80s. But we do have other stations out there. The Europeans have stations, the Russians have stations. And then Mauna Loa at the top of the volcano in Hawaii. So basically, is an observatory. And the reason they have that there is that in the middle of the Pacific, we've got pretty good mixed and unpolluted, maybe I should use a better word there, but let's say less polluted air because there's very little around there that could put industrial pollutants into the air. So what we see here, again, carbon dioxide going back into the 1700s, starting off around, let's say about 280 parts per million. We call that the pre-industrial levels of CO2. And over time, increasing, and then whee, look at this, increasing very quickly as we get past the period of World War II, where lots of the world was industrializing very, very quickly. Again, here you see that up and down pattern by the year from the 1960s all the way through current year. And this is on the top of the Mauna Loa volcano. So those had direct measurements from the 1960s and up through today. So that NOAA is doing those measurements now, National Oceanic and Atmospheric Administration. Prior to that, Scripps Institute was doing the measurements, but basically a continuous record. And we see a trend up. So now, instead of that 280 parts per million pre-industrial levels of CO2, we are way over 400. In fact, we're over 410 now and increasing by 2 parts per million per year. That's a problem. That's an issue. We have to find ways to adapt to this new CO2 levels. 2016 all the way through 2020, and what we see is that up-down pattern maximizing in May of each year, and probably around October we're finding our minimums, but the trend line is we are increasing in our CO2 concentrations. January 2020, about 413 parts per million, and I believe the measurements for February were a little higher than that, 414 parts per million. Now, if you look at January of 2019 versus 2020, that's showing an increase of about 2.5 parts per million per year. Now, linking with temperature, we can see going back to the 1880s, we see temperatures increase. Now, of course, it's up and down pattern here. It's not completely linear, but we see the trend line here is very much increasing in temperature, and we're starting to increase at a much faster pace. So we are increasing quite quickly in our temperatures. Now, I know it's hard to see this, and in fact, because I'm covering a very important piece of data here, I'm going to have to explain that to you. The year that was shown over here is the warmest year on record within the time that we've ever been taking temperatures as humanity. This is the year 2016. So the warmest years on record, going from warmest through getting progressively cooler, 2016, 2019, 2015, 2017, 2018, 2014, 2010, 2013, 2005, 2009. These are going all the way back to, let's say for decency's sake, the 1880s or so. What that means is that every single year that is in the top 10 hottest years globally recorded are all within the last 15 years. And 5 of them, the top 5, are in the last 5 years. That's problematic. That's showing that all of us now, we've grown up, and especially you as students, you've grown up in a time that is not normal. You've grown up in an abnormal time in terms of lower atmospheric temperatures. It feels normal to you, but it's not really normal. It is abnormal, it is weird, hence the climate is getting a bit weird. That's why I like that word, or that phrase, climate weirding. But the common phrases, climate change or global warming. So besides the lower atmosphere warming, which is an obvious consequence of climate change, we also see that storms, especially tropical storms, get more energy and therefore they're going to be more intense. Glaciers are going to be melting more frequently and more quickly, and that's the result of the air around them being warmer. Glaciers, of course, when they melt, turn into water, and that water goes downhill, and downhill, for the most part, ends up being the oceans, so sea levels rise. Now, the seas are also warming up, so thermally, the water expands, also allowing the ocean surface to get higher. Loss of farmland means that there's some places where we used to depend on moisture for crops, and we can't depend on that moisture anymore because the places where water will fall or rain will fall is going to be different now that the air is warmer. the flow of air is going to be impacted. So places that used to be wet might become dry. Places that were dry might become a little bit more moist, or they could be even drier. So it's an experiment that we're learning as we go along. So seasonal weather patterns can become more extreme, or they could become less dependable. And the upper atmosphere we're going to see is actually going to cool a little bit. We'll cover that a little bit later on. So some of the other effects, wildfires. We see basically in the 1950s through the 2000s that there used to be 60, 70 years ago, very infrequent fires in North America, and now so many more fire episodes. Why? Because we're getting more flooding and more dry seasons, and during that dry season, things dry out significantly. Add a flame to that, and things burn like crazy. So drier air, warmer temperatures, those are ingredients for wildfires. For Europe, we see that, let's say back in the 50s, very few wildfires there, and a lot more in the 1990s and 2000s. Same in Africa, that trend line, Asia, and Oceania, which is basically Australia, New Zealand, New Guinea, etc. So wildfires way more common. December 17, or December 2017, we had a lot of fires in Southern California. The Thomas Fire, the Rye Fire, Creek Fire, Skirball Fire, all these blazing at the same time in December. And that would not have been a very typical situation a few decades ago to have wildfires in December, especially ones raging like these did. Fires with flames pretty much because of the winds burning horizontally all the way to the ocean. That was a very, very scary situation for many people there. This is in the neighborhood of La Crescenta heading towards Sunland, Tujunga, and again, the smoke is moving horizontally, and the flames did the same thing. So this is not a typical thing for December. And we'll see in a few minutes that oftentimes dry, fire-prone conditions can sometimes be followed immediately afterwards by the opposite, cool, wet, and flood-prone conditions. Speaking of floods, back in North America, or actually that's North and South America, so the Americas, infrequent floods become very frequent floods. Same in Europe, Africa, and Asia. Same in Oceania, and especially Australia, very prone. And in recent years, New Zealand very prone to floods that they didn't get before at all, not of that magnitude. So we can go, this would be 2014. We would see that this is a marina, so boats would normally be here. And so some of the marinas and some of our dams and reservoirs were drying up to worrisome levels, so that water rationing became the norm. Shortly afterwards, we get rain. So this is January 2018. Again, this is just after the big fires of December 2017, and all of a sudden massive flooding. So we're not just concerned with the fact that the lower atmosphere is warming. It's all these follow-on effects that we seem to have average temperatures increasing, certainly, but we're not really getting average anymore. We're getting extreme conditions on both sides, but especially extreme conditions on the warmer side. That's changing the energy flow. It's changing the moisture regime and the flow of moisture in the atmosphere, and that's going to mean flood, drought for many areas of the planet, especially the Los Angeles area. So in this diagram here, this shows pretty much a statistical analysis of events, and if they were categorized in the period of 1950 to 1980 as being normal on the extreme side of hot and on the extreme side of cooler than normal. And we'll keep that green line there as we go through the next few slides. And we can see that as we got to the 80s, all these events were shifting off to the warmer side of where they were in the 1950s through 80s. Continue on here into the 90s, and now we see shifting even more to the right. We start to pick up some extreme events. Into the 2000s, now we're really shifted. What that's telling us is that we're getting a lot more of these extremely hot temperature events. We're getting a lot fewer of these extreme cold events, and we're not seeing too much of what we used to consider to be average. Now we are basically living in a very warm time compared to the past. So extreme temperatures used to cover 0.1% of the Earth. Now they cover a full 10%. It's quite worrisome. Warm up, glaciers melt. So what's happening? Our sea levels are rising. And as the sea levels rise, both from glacial melt and runoff, and also because of the thermal expansion of the water themselves, we can see that the oceans, the higher up we go here, that's showing the oceans are getting higher and higher and higher. But also they're getting higher faster than they used to do. Now we're getting about or over 3 millimeters per year added on to the level of the ocean. So that's the old trend line there, about 1.8 millimeters per year. Then we get into, sorry, if we go to the early part of that, it was less than a millimeter per year. Then we go to 2 millimeters per year, and now about 3.2 millimeters per year. So the oceans are rising faster than they used to do. A total of about 8 inches, approaching 9 inches so far. And projections are we might triple that or more by the end of the century. Ice caps melting. These are not glaciers here. This is sea ice. Glaciers would be found on Greenland over here, but the sea ice is very important too for habitat for organisms, but also to give it a little bit of an idea of the state of the planet. We can see here, 1979, plenty of sea ice, but by 2003, very little. So this area here used to be iced up, is now melted. In 1979, 2007, 2012. Now, another effect of this is this area used to be impossible for people to go and exploit resources from, such as drilling for oil. So as this has become ice-free, now not only are people able to navigate this area, but they're also starting to drill for, you guessed it, oil and gas and other natural resources, which will contribute to the CO2 of the planet. This is a graph of glacial, this is of Arctic sea ice, and that sea ice, again, diminishing over time. There could be a time where we don't have sea ice in the Arctic any longer. So what are some of the benefits of doing some personal or making some personal choices that would minimize the impacts of climate change? I think it's pretty clear you cannot stop climate change. It's going to be here with us. What we can do is minimize how those changes are going to be, or well, let's say just how bad it can be. So you could choose to do some things like take public transportation instead of taking a car. You could fly less because airplanes use up an awful lot of fuel, but at the same point, it takes a long time to get to faraway places otherwise. Preserving rainforests, that's something we probably all want to do. Sustainability, that's a goal we should all try to achieve, where we utilize resources and basically only the rate that we can have them rejuvenate. Green jobs, well, that goes hand in hand with putting solar panels on houses. I put a solar panel array on my house a few years ago. With the tax credits, it came to about $6,500. My electricity bill got cut in half to a third. So I'm reaping the benefits of that for 20 or 30 years. The cost of solar panels came right back, and somebody had to put them on there. So that was a job for somebody to install those. It's nice to be in livable cities where the air is breathable. You can get around by public transportation. And of course, Glendale offers pretty good air quality compared to what it used to be, but it certainly can be better. Renewable energy sources always better than non-renewable. Clean water and clean air. These are goals that we all have, not only for ourselves, but also for our children, because we want to leave them with a healthier planet too. And to tell you the truth, the generation I'm in, we didn't do the best job. We could do better, and we can continue to do better. We all learn as we go along. I've been teaching this class for almost 30 years now, and I finally get the sense that for many of these issues, people are taking them seriously. Initially, that was a very hard job to be talking about climate change and finding that people were actually taking that to heart. All right, we moved away from carbon dioxide. Methane kind of wrapped them up into a single conversation about climate change, and another trace gas, ozone, ozone O3. So ozone is found in two major parts of our atmosphere. It's found naturally up in an area called the stratosphere, so we call this stratospheric ozone, but we also get ozone as the byproduct of pollution. and that's in the lower atmosphere, which is referred to as a troposphere. So we have tropospheric ozone and stratospheric ozone. Stratospheric ozone is natural and good. Tropospheric ozone is a pollutant, not good. So we call that bad ozone, and this would be good ozone. So we differentiate the two types of ozone as good ozone and bad ozone, or stratospheric ozone and tropospheric ozone. The first one here is stratospheric ozone. That's the natural good stuff. It's formed naturally over the past 3.5 billion years, found about 8 to 28 miles above our heads within that zone called the stratosphere. And that's our natural sunscreen. It's basically going to shield us from the sun's damaging ultraviolet rays. Some of them still get through. That's why we get sunburned. But if it wasn't for this layer, we would really get burned to the point of really not being able to survive. The stratospheric ozone accounts for 90% of all the ozone supply on the planet, the natural ozone supply, but it is under threat. Since the 1940s, it's been under threat, but we didn't really realize this until we got to the 1980s. More on that to come. So natural ozone forms when sunlight splits natural oxygen, or O2, into two individual oxygen atoms. So the bond between those two oxygen atoms, between that oxygen molecule, is split, frees up these oxygens, and they can recombine as O2, but they'll get split again. But if they recombine, if one of these recombine with an O2, so O plus O2, creates a molecule with 3 oxygen atoms, we call that ozone. That's the natural stuff. Up in the stratosphere, that's the stuff that's our natural sunscreen. So this forms and is stable up at higher elevations in that stratosphere. This won't get split by won't get split by sunlight. What it will do, though, is absorb some of that ultraviolet radiation and warm up a bit. Tropospheric ozone, on the other hand, still the same stuff. It's still 3 atoms of oxygen bonded together into a single molecule called ozone. It's just in a different place, so we call it tropospheric ozone. It is in the wrong place. It's basically a component of smog. It's toxic. It's going to make your eyes irritated, your throat sore, irritate your respiratory tract. It's also a greenhouse gas. It's so toxic that it is used to treat sewage and kill the bacteria and viruses even inside that sewage. So it's pretty nasty stuff. You don't want to breathe ozone. You certainly don't want to be exposed to it for too long at all. And that's one of the reasons why avoiding smoggy days is a good thing. So chlorofluorocarbons, or CFCs, very small concentration in the atmosphere, a trace concentration, but a few of these molecules can do an awful lot of damage to natural or good stratospheric ozone. First of all, where does it come from? Well, it's man-made or human-made. So in the 1940s, chemical companies had a lot of byproducts from the petrochemical industry. They needed to find ways to utilize these products, otherwise they were waste. So they would stick chlorines and other molecules onto hydrocarbons and see what they did. They experiment with them. And one of the things they came up with is chlorofluorocarbons. So it's a long chain with carbon and oxygen and hydrogen and fluorine and chlorine, etc. So these long chain carbons or hydrocarbons were modified, and they would act in different ways, and sometimes with positive consequences. So from these experiments came multiple solvents that could be used to clean circuit boards very well. One in particular could be used as a propellant. So you get a liquid, you send this gas through it, and it disperses the gas very, very well. So for spray cans, that was a very good use for those particular chlorofluorocarbons. But the one that was mostly used was one called Freon. And Freon had the ability to compress and change its temperature enormously if you compress that gas and then release that gas, and the temperature would cool down very quickly. So it became a very good gas to use in refrigeration. So if you notice on one side of a refrigerator it's very warm, that's where the gases are being being compressed. And on the other side, we have where the gases are being expanded in a sealed area. If that sealed zone is made out of metal. As the gases expand, they cool the metal. The metal could have air flow upon it, and you get a cold air environment from that. So basically, from a compressor to the expansion, we get a cooling system. So refrigeration, freezers, air conditioners are all used or utilize gases such as this. What we didn't know until the 1980s was that these same gases, when they leaked, just naturally leaked out of a system because the seals weren't 100% effective. This gas, the CFCs, would migrate up in the atmosphere. They were a solvent or a little lighter. They would migrate up into the atmosphere. And if they were hit by sunlight at very cold temperatures, that molecule would shatter and basically release the free chlorines into the atmosphere. Again, we didn't realize. So basically, the CFCs over here get hit by sunlight. And if we have cold temperatures plus sunlight, like we do in the Antarctic springtime, we see these CFC molecules being broken apart, shattered to release the chlorine molecules. The chlorines will go and find an O3 molecule in the stratosphere and pull that apart. It's basically going to pull that ozone molecule apart over here, and that ozone molecule gets split up into O2, and the chlorine stole one of those oxygens. After a while, that chlorine will dump that oxygen molecule and try to find another O3, another O3 over here, split it apart, break it up, release the oxygen. This cycle could go on for tens of thousands of times with a single chlorine molecule splitting up many O3 molecules. So if we have enough of these chlorine molecules in the upper atmosphere, we will see a reduction in O3 levels at the expense of O2 and oxygen. So ultimately, when the free oxygen is released, it will try to find an O2 and form O3. Excuse me. So what we see is chlorine molecules pulling apart O3, and we also see oxygen and O2 being reformed. At the current rates we were seeing for many, many years, the rate of ozone destruction exceeding the rate of ozone repair. But recently, we're starting to see some changes to that. And the reason for that is that in 1987, 38 industrialized countries agreed that we're going to do away with the production of CFCs, do away completely. And it took place at the end of the 1990s. We did away with the non-essential use and production of these CFCs. Now, production was halted, but we still find out that people are using Freon as an air conditioner coolant in older cars. Newer cars don't use those same CFC molecules or Freon anymore. So looking back, NASA had flown over the Antarctic, and the reason the Antarctic is important is because upper air flow brings air and therefore molecules above the Antarctic. And in the early spring in the Antarctic, the sun comes up for the first time in 6 months. So basically you get to September and the sun comes up, and that's the sledgehammer that breaks apart the accumulated CFC molecules, frees up the chlorines to go and damage or break up as many O3 molecules as they can. We've been monitoring this, and with the flyovers and also ground-based observations, we can see what's been going on since the 1980s. Now, if you see colors that are, let's say, in this reddish or almost purpley color and blues, these represent low levels of ozone, so that's bad. If you get the lighter blue and into the green shades, even in the yellow shades, that's higher levels. It's measured by Dobson units, so a higher Dobson unit reading is better, a lower Dobson unit reading is worse. And what we see going from 1980, 82, 84, 86, 88, etc., all the way in this diagram to 2001, is that we used to get very few in that blue, or very few readings in the blues and reds, and now look at this as we progress through time. It's getting progressively worse, so we're getting a hole developing in the ozone. Now again, it wasn't until 1987 that we decided we'd do something about this, but those molecules stay around in the atmosphere for over 100 years. But if we put less of them in the atmosphere, then we allow the oxygen to repair back into O3, then we'll see that the system, the natural system starts to repair itself, and we see a better situation developing. So let's look here. Worst case scenario, 2006, the ozone hole got to a size of 29.5 million square kilometers and very low Dobson units at 82 Dobson units. We initially thought that we would reach a low point around 2020, 2025, but it looks like we reached that in 2006, because if we look at more recent readings here, so remember that 29.5 million square kilometers, 82 Dobson units. This is lower number bad, and this one, the higher number bad. So we want a smaller hole, and we want more ozone readings, which would be a higher Dobson unit number. September 2017, 20 million square kilometers, so that's a smaller hole, and the Dobson units were more robust. That was the smallest hole we had since 1988. 2018, well, it got a little bit larger again, but the Dobson units were still not as bad as not as bad as 2006. 2019, 16.4 million square kilometers. It was the best since the 1980s, and we have better Dobson unit readings here. So I think that most scientists would agree that the trend is looking pretty good for the repairing of the ozone hole in the Antarctic, and that shows that we can collectively do something when we all put our heads to it and make it our common goal. Maybe climate change will be the next thing on our list. I put in red here, 2006. Maybe that's an exam question for my classes. When did the situation with the Antarctic ozone hole reach its worst case scenario so far? Of course, that would be 2006. Okay, oxides of sulfur, oxides of nitrogen, and their relationship to acid deposition. I'll make this. Okay, so sulfur oxides, very small concentration, just a trace. Sources, swamps, oil drilling, etc. It's an impurity in coal, because within the swamps where sulfurous bacteria occur, when the coal forms, those impurities get caught within the coal. It can range anywhere from about 1% to 5%, depending on where the coal is from and the type of coal. When we burn the coal, we release the carbon dioxide. We also release the sulfur compounds, and those sulfur compounds go up into the atmosphere. They mix with water and form sulfuric acid, and sulfuric acid will then get entrained in the wind pattern. So downwind, where we have rainfall or snow, we get acid rain or acid snow or acid sleet, etc. And that acidity can be very damaging to forests, can be very damaging to lakes, to cities, etc. Forests get killed, ecosystems get destroyed, monuments get eroded away at a much faster pace than normal. Nitrogen oxides, well, nitrogen also comes from burning of material burning of fuels at very high temperatures, but also naturally as part of the nitrogen cycle. Now, the nitrogen oxides do remain up in the atmosphere for quite some time. Agriculture is a big producer of these nitrogen gases, so we can't minimize that impact also. Nitrogen oxides are not only a greenhouse gas, they're also the second gas responsible for acid rain. So the two gases responsible for acid rain are sulfur oxides and nitrogen oxides. Collectively, we call those NOx and SOx, or SOx and NOx, because SOx would form sulfuric acid, a much stronger acid overall than NOx forming nitric acid. So again, SOx much more associated with acid rain than NOx, but those are the two gases responsible for the process. So here we see some of the impacts here. So dying forests, fisheries die off, and we also see acids effect on monuments and buildings. And this would probably have been, I don't know, 50 years or so. So maybe some Renaissance art out there for many, many years, and then after industrialization, the effect can be seen. The effect of the acid rain can be seen quite dramatically. Always, if we have industry, the place most affected will be downwind. So for European industrialization in Great Britain, France, and Germany, those wind patterns would have come across Great Britain through France and Germany and then swept up towards the north. So we get Sweden and Norway having a lot of impact from these acidic rainfall events. In the United States, on the west coast, we have quite well, let's say we don't have as much of an acidic rain issue as we do on the East Coast, and largely because the winds are coming in from the west, moving over towards the east. We have lots of industry just in the Great Lakes area, and that industrial pollution would traditionally move towards the north, following the wind patterns and into Canada. So Canada got a little bit angry with us over this, and we're very happy when we start to have some regulations that would limit the production of NOx and SOx compounds moving their way. Most of the SOx, sulfur oxide components in the United States, are produced when electric utilities burn fuels, especially coal, to produce electricity. And for the NOx components, it's largely from transportation and agriculture. Again, sorry that I'm covering that over here. All right, moving on away from our gases now to the vertical structure of the atmosphere. Well, the main way that we differentiate the layers of the atmosphere, moving from the surface up, would be based on what happens to temperature as you change your elevation. So I have a separate video on this. I'll give you the link for that. And it's about 17 minutes long, but it explains how we differentiate the lowest layer, called the troposphere, and then a boundary zone called the tropopause, then the stratosphere, the stratopause, and then finally the mesosphere. Once we get above the mesosphere, we're pretty much dealing with outer space here, because 60 miles or so above the surface of the Earth, nobody lives there, of course. And this is really the realm of astronomy more so than geography. What I really want you to know are the different layers going from bottom up to about 50, 60 miles, troposphere, tropopause, stratosphere, stratopause, and mesosphere. I won't waste the time right now to differentiate those layers. I will instead have you check on the video, which is under modules in your Canvas shell. So that's a separate video, but please do look at that. As we get towards the end of this chapter, we do address weather versus climate. You've heard these terms many, many times. Weather refers to the atmospheric conditions for a specific place and a specific time. That means the weather is different from one place to another. And also the weather changes from time to time. So at the beginning of this video, the weather was actually different than the weather at the end of this video, because it's taken just over an hour to do this. Now, how do we measure these atmospheric conditions in terms of weather? Well, how hot or cold is it? So temperature, was it raining or not? Precipitation, windy or not? So we talk about wind speed and wind direction. Was it humid or dry? Was it cloudy or clear? Was the atmospheric pressure high or low? So these are all different ways of measuring the weather. Again, the short-term atmospheric conditions for a specific place and a specific time. Now, climate is also a description of atmospheric conditions, but not for a specific place. It's for a large area, which we call a geographic region. So let's say the climate for Pasadena, Glendale, Northridge, as part of this large region, are all pretty much the same. So the atmospheric conditions for a large region averaged over a very long time period, so probably over 30 years, but also accounting for maximum and minimum amounts of precipitation, maximum and minimum temperatures throughout the year. In terms of monthly averages for the warmest month, what's the warmest temperature of a particular place averaged for that month, and what's the coolest temperature, what is the average temperature of the coolest month? Again, my words all mixed up here because I'm getting a little bit tired and it's getting late. I'm trying to do this in one take too. So basically, weather, atmospheric conditions for a specific place and a specific time. Climate, atmospheric conditions for a large region over a long time period. For climate, the two main variables we use to measure it would be precipitation and temperature. So what is the average temperature? What is the average temperature of the warmest month? What is the average temperature of the coolest month? Again, for the precipitation side of climate. What is the total amount of rainfall that falls in a year? What is the average rainfall in the wettest month? What is the average rainfall in the driest month? If we had that data, we can start to figure out what type of climate a place might have. So what makes weather and climate different from one place to another? Well, we're going to see these 7 factors pop up many, many times. So the latitude could make 2 places different. One place could be hot, one place could be cold because they're near the equator or further away from the equator. Elevation. One place could be high in the atmosphere or high in the troposphere, and another one might be lower. So one has high altitude and one has low altitude, or high elevation, low elevation. Distance from a large water body. One place might be close to a coast and therefore have moderate temperatures. One place might be very far away from a coast and therefore the air would be very dry. And in that case could see warm temperatures in the summer and pretty cold temperatures in the winter. Could also have warm temperatures during the daytime and very cold temperatures at nighttime. The general circulation of the atmosphere. Some places are under high atmospheric pressure most of the time and therefore clear skies. Other places are under low atmospheric pressure most of the time and therefore with rising air associated with low pressure, they could be very cloudy and that's going to influence the temperature regime during the day and during the night. The general circulation of the oceans means that our oceans do circulate. In the northern hemisphere, they circulate in a clockwise pattern, and that takes energy absorbed in the tropical Atlantic Ocean. Is going to come along on the coast and head all the way along the eastern seaboard of the United States and keep on going, taking that heat energy all the way to places like Ireland, Scotland, Norway, making those places warmer than what they should normally be. Topographic barriers means that on one side of a mountain, air seems to move upward, cool as it goes up, form clouds, and those clouds could precipitate rain on one side of the mountain. On the other side of the mountain, the air sinks down and we get dry conditions. So depending on what side of a mountain you're on, will give you different weather, different climate. And finally, storms, to make it easy. There are places where storms tend to hit quite frequently and places where they do not, because storms have a specific track. And we can see how often these storms move into certain areas, so that a place like Seattle in the northwest corner of the United States, the Pacific Northwest, there's a lot of storms in the wintertime, a mild amount in the springtime, and a few in the summertime. Whereas Los Angeles on the same coast, out of the storm track, doesn't get all those wintertime storms, gets very few in the fall, a few in the spring, and almost none in the summertime. So this track of the storms could certainly impact the weather and the climate in terms of both temperature and precipitation. Now, I've done an in-depth look at these same factors in Chapter 3 when we look specifically at temperature and how these same 7 factors influence that. I encourage you to take a look at the end of Chapter 3 in order to look at these in greater detail. So there we go. I think we're getting towards the end of this chapter.